lecture 4. Quick recap of what we were doing last time. So we were discussing the problem of finding maximal in 2 dimensions, and I did come across a few questions later regarding what happens if we do the maximal in 3 dimensions. How do things change? And it turns out that in 3 dimensions the problem is of course a little bit more difficult. As you grow up in dimensions, problems become more difficult, but the algorithm remains n log n. So, in 2 dimensions we have n log n, in 3 dimensions we also have n log n. So, what I will do is I will not go through that particular problem in the class in 3 dimensions. I will make it into an exercise problem, okay, and I give you enough hints so that you should be able to solve it on your own. And you can solve it essentially using the technique that we discussed. Okay, let me just recap that. So, we discussed essentially 3 techniques. So, one was the traditional divide and conquer. Then we discussed something that was well, I did not give it a name, but when we started scanning from the highest x coordinate towards the lowest x coordinates and maintained some kind of information, okay, as we move from the highest to the lowest x coordinate, maintain the information about the highest y coordinate, right. So, the basic principle of solving the problem in using divide and conquer or using this scanning from right to left was the same. That is, the information required was maintaining the highest y coordinate of the points that have higher x coordinate, right. So, we were looking at it from right to left. So, this particular technique, so one reason that I actually use this problem is not because the problem in itself is a very useful problem, but it has of course some applications, as I said, but more so in terms of some of the algorithmic techniques that we will use later for other problems in computational geometry. And so, this particular technique where we going from right to left has the name of line sweep. Okay. So, I will expose that technique using another problem today. So, line sweep is what we used, and if you use line sweeping in 3 dimensions, okay, then you can actually match that n log n algorithm in 3 dimensions also. The only the complicated part or the one that you have to rework is that when you again so you sort, let us say, along x axis. So, you are going to sort along one of the axis. So, here also when you have 3 coordinates, suppose you sort along x axis and then start from the maximum x coordinate towards the lower x coordinates. At any point of time, the points that you have already scanned, okay, cannot be dominated by the points that you have not scanned. That remains. Okay. But then you have to somehow maintain some more information about the points you have scanned so far, because now you are dealing with 3 coordinates and not 2 coordinates. Okay. So, the current point that you are scanning, okay, has a lower x coordinate than the other points, but it also must have a lower y and a z coordinate for that point not to be maximal, right. So, this additional information needs to be stored in a way so that you can quickly process each point. Right. So, in the case of 2 dimensions, it was just one information, highest y coordinate, right. Here it is somehow it is not simply highest y coordinate and z coordinate, it is a mix of both. You cannot separately look at the highest x and highest y, because they may belong to 2 different points. So, the same technique of just storing the highest x and the highest y is not going to work. So, we will have to kind of store more information in terms of not just 2 points, but actually it is going to be. So, if you have to think about it, it is going to be actually a chain itself. Okay. So, it will be like a cross section. So, you have to first imagine how the 3 dimensional maximum looks like. So, in 3 dimensions the maximum will look like again some kind of staircase, but it is a 3 dimensional staircase, and what you are going to store is a cross section of the 3 dimensional staircase. Okay. And you have to store it in a data structure, so that you can quickly process a given point let us say in about log n time, so that eventually you can match that n log n bound. Okay. So, this is something that I will leave as an exercise with some hints for you, but it is interesting that you should get more experience in terms of visualizing some of these problems and solving it using line sweep. Okay. And of course, the last technique I discussed was something that was sensitive to the size of the output, and this is very typical of only geometric problems, that the running time, if you can make it sensitive to the actual output size, then we get something that is something that is desirable, because then we are trying to match the best possible time both in terms of input and output sizes. Okay. So, this n log h bound, where h is the output size and n is the input size, has order n running time when output is small, and when output is large, let us say even about square root of n, you have about n log n running time, and it can also be shown that this is optimal. So, I will just make just a few more remarks about this last thing, this n log h algorithm. So, the way I analyzed it was writing a recurrence, right. So, this is the recurrence that I wrote. Yeah. So, this is the recurrence that I wrote, T's of n equals O of n, the next one, that was only in terms of input. So, T of n comma h, where n is the input and h is the output size, although both h is unknown, I can still write this recurrence, and then I claim that you can prove rigorously that it has a running time, and this recurrence has a solution of n log h. Okay. So, this is one way of proving this bound. There is another way, and let me just give you some hints about it. So, so your maximal looks like finally the output is like the staircase, okay. And when we say that the output side is h, okay, essentially there are h points here. So, I can call it let us say the output 1, output 2, output 3, all the way up to let us say output h, okay, and this is some output I, let us say. So, these are the points. So, there are h points the output, all right. And the remaining points must be essentially under the staircase, okay, and they are distributed in some fashion. Okay. So, this is my x axis, this is my y axis, okay, and the remaining points which are not maximal, okay, they appear under the staircase in some way. Okay. Now, if you focus on just any of this, a single step of the staircase, for instance, let us say we are looking at this. Okay. So, all the points specifically just under this step. Okay. Let us say that there are about n sub I points. So, under the ith step there are n sub I points. So, there are n sub 1 points here, there are n sub 2 points here, and so on and so forth, okay, and there are n sub h points here. Now, the way that we solved the problem, that is you found the median line, okay, wherever is the median line. So, median line, and we calculated which is the step that crosses the median line, right. And how did we do that? We simply just looked at all the points to the right of the median line, found the highest y coordinate, and we could compute this particular step, and then we did the divide and conquer. It was not a real divide and conquer, because eventually we just had to paste. So, this actually has a name in literature called marriage before conquest. I do not know how it can happen, but so even before you have actually solved the problem, okay, you have that how they are going to be pasted together. Okay, rather than first solving for half the points, solving for other half points, and then somehow trying to merge that the way that you do it in merge sort. Here you actually figured out that this step is the one that crosses the median line, and I only need to, whatever solution I compute to the right of it and to the left of it will simply just be pasted together. Okay, so, I have actually married them even before I have actually solved the problems in the two halves. It is called marriage before conquest historically. So, then so these points that are under these steps, at some point the moment you discover that step, certainly all the points below that step, so here all the points that fall into this region should disappear the moment you discover that step, because we know that there can never be the maximal points, right. So, now the question is that if you look at the ith step, okay, there are n sub I points under it. Of course, all these numbers are unknown to us. We do not know anything about n1, n2 or even h. Okay. But we certainly know that the moment the ith step will be discovered, those points are going to disappear. Okay. And certainly these points the moment I actually somehow manage to, so initially started with the median line. So, this the median line. So, the moment, and then I am going to find the median of the two halves. Okay. So, next time maybe this will be the median line, this will be the median line. Okay. But the moment I have a median line going through this block of points, okay, these block of points are not going to survive after that, right. Do you see what I am saying? So, initially of course, the median went through this block of points. So, this block of points have to be handled at that point and they will disappear, because that step will be discovered. So, if you think about this cluster of points n sub I, okay, the moment we have a median line going through that cluster, okay, at some point, because the divide and conquer, we will break that cluster, right. We will have a median line going through that cluster by just carrying on the recursion, right. So, the moment it goes to that cluster, okay, those points need not be processed any further, because at that point we will know that these are not the maximal points and they will actually be eliminated. Okay. So, we only need to handle these points as long as we have not chosen any point from that cluster for the median computation. Okay. So, okay, let me just illustrate this. So, I have, let us say, of course, I do not know those clusters of points, but just hypothetically I have a large cluster of points, let us call it some n sub I. Okay. So, there are some points under some step that is going to be discovered sometime in the future. Okay. How long can we will not how long can this point survive? Certainly not beyond when we have some median line going through this cluster, right. So, question is how long can these points survive without being processed, I mean without having been split up into into two sets. Remember that a median line splits a point set into two halves, more or less equal halves. So, if this has n I points, how long can these not be split up, because you are doing well something more specific than that. Yeah, right. So, essentially what we are saying is that suppose the n I points survive for j iterations or j levels of recursion, let us say. Right. So, what can we claim about this j? Every time we do a recursion, the size of the sub problem is halved, right. So, at the jth level of recursion, the size of the maximum sub problem can be n over 2 to the power j. Okay. And so, this is the size of the sub problem, maximum size of the sub problem. Okay. And the cluster has size n sub I. So, what is the relation between the cluster size and this maximum size? If the cluster has to survive, then this cluster must have size smaller than that, or what, larger than that, smaller than that, right. Otherwise, it is definitely going to get split up. You can't have any sub problem larger than n over 2 to the power j. So, this cluster should have, so if it has to survive j recursion, then this should exceed the cluster size, right. Or in other words, j should be smaller than or equal to, let us say, to n log of n over n sub I. So, what we have established is that we can't sort of this cluster cannot remain cannot survive beyond j iterations, and j has to be less than. So, it can only be processed for so many steps of the recursion. Now, if you think about it, what is that we are doing? I mean, it is very similar to quicksort kind of thing. At any point of time, the the processing that is being associated, you can think about it like that every point is essentially being compared with something, okay, whether it is to the left of the median or right of the median. Okay. And when you do the processing, of course, median finding is linear time. So, you can think about charging the cost to each point. Okay. So, at any level of recursion, the total cost for division of the problem is linear, or in other words, you can average it out as order 1 per point, right. It is order 1 per point. That is another way that I can sum up the cost by looking at the total charges accrued by each point at the end of the algorithm. Okay. So, the initial step, we did the median finding, we did the divide step. Okay. The total amount, the total work that we did was order n, okay, and there were n points. So, if you average it out, you charge the average cost to each point, okay, then it is going to be order 1 per point, right. So, similarly, at every level of recursion, a point can be charged at most order 1. If the point survives, if it disappears, if the cluster breaks, the point is gone, I do not need to charge it anymore, right. So, if it survives for at most so many iterations, so a point in cluster I can survive for at most so many iterations, okay, which means that the total cost of algorithm, total running time, can be bounded as sum over I for all the I clusters, okay. And for each cluster that has n sub I points, the cost is this log of n over n sub I, right. So, I can simply just say n of I times log of n over n sub I equals, you have, if there are h output points, is this. Okay. So, no complicated recurrences, no 2-dimensional recurrences, nothing. Now, then again, not so, but then it still looks like a fairly it's not a very transparent formula. What is that we have achieved, unless some people have seen it before. So, this actually has a very nice connection with what is called multiset sorting. Multiset sorting means if you are sorting some numbers where there can be repetitions. Okay. So, there are, let us say, there are h kind of h different values, okay, but there are n elements, okay, and let us say there are n sub I elements of the ith kind. Okay. So, sorting actually becomes easier if you have lots of elements which have the same value. For instance, I mean, the trivial case, all elements have the same value, then sorting is absolutely trivial, right. In one step you are done. Even if they have two kinds of values, you can still argue that just by doing one iteration of quicksort you are done actually. You just have to divide it once, all the zeros and all the ones will be clubbed together. So, it is constant time. So, you can see that if you repeat points, or repeat values, sorting actually becomes faster than n log n. So, and this is essentially the formula that you get if you have seen that before, that if I have n I points of the ith kind, elements of the ith kind, then this is the running time, and this is always, this is again you can prove fairly easily, this is always less than n log h. And in many cases, depending on how the distribution is, okay, this could be much better than n log h. So, what we have actually argued is a bound that is even superior to n log h, but it uses a further finer parameterization of the point set, that is how many points is below every step. Okay. So, this formula uses even more characterization of the point set than the n. See, the n log h uses more characterization in the sense that I am taking care of output size plus input size. Okay. The formula that I just derived, has even finer kind of characterization, that I know how many, we do not know, but we are making use of number of points below each step. Of course, none of this information is required in the algorithm. The algorithm does not know anything about either h or the number of points on every step. It is just that in the analysis, this falls out. Okay. And this formula, this thing, the nice thing is that this is actually bounded by n log h. So, I do not have to separately prove that this is n log h. This is always bounded by n log h, and in many cases it is better. Okay. So, I will just conclude with this observation about the 2D maxima, and I already mentioned that 3D maximal can also be done in n log n time using no, just a more refined implementation of the line sweep algorithm. Okay.
So can you give some insight into why this formula sigma ni log n h, that is the cost of a multiset sorting? And you said that this is for multiset sorting where there are
yeah, this is a lower bound also. So you just have to open Knuth and see. Yeah, yeah. But of course, for a problem in geometry, if you want to prove a lower bound, you have to work much harder. Okay, so I will not. I'm not sure if I could get that far in this course, but I will talk about lower bounds maybe in 1 or 2 lectures. I'll draw your attention to these kind of things. Okay. But this bound is a classical information theoretic bound. Okay, so. So today I will introduce another problem, and I said I want to basically expose this method of what I am calling line sweep a little bit more. So consider the following problem. I have given a set of line segments. Don't confuse that line segment with this line sweep. This is just the name of a method. Though this I have given some line segments. Okay. So let us only look at this rather small set, because otherwise it could get cluttered up if I draw them. Now, the goal is that given a set of line segments, so we want to compute the intersecting pairs. So I can name them. I can call this S1, call this S2, S3, S4, S5 and S6. So there are 6 line segments in this particular figure, and we want to compute the intersecting pairs, which means in this case I want to report at the end of the algorithm S1, S2, this is one intersecting pair, S2, S4, S3, S4, S5, S6. So there are 1, 2, 3, 4 intersections. So there are these 4 intersecting pairs. Okay. So how would you algorithmically try to compute these intersecting pairs? First of all, let us just for a moment reflect on how do you, given 2 line segments, how do you compute the intersection? This is a very basic question. How do you compute intersection between 2 given line segments? How are the line segments described? How would you describe them? The 2 endpoints, right? The natural description is look at the 2 endpoints, the 2 line segments. So your input is given in form of two pairs of points, the endpoints, the each line segment. So 2 pairs of such pairs. So how do you just compute given the intersection of 2 line segments? So that's, it somehow must be the primitive, right? So just tell me yes or no. I mean, it can be done, right? Yes. Okay. Great. So whether you remember your analytical geometry or not, you should know how to compute the intersection of 2 lines, and therefore you should be able to figure out whether 2 line segments intersect, right? If both the points are to one side of the line containing the segment, they do not intersect, otherwise they intersect. Okay. So some formula, simple formula, basically it is solving a pair of linear equations, right. So, that is it. Okay. So, there could be degenerate cases of parallel lines and coincidental lines. So, all those things I am taking for granted that we know how to handle them. Okay. All the special cases.
If you solve the equation of the line, you get whether the extended line will get, but
right,
that will be in
right.
line
So, after the extended line, it is very easy to find out if both the points are to the same side or not. So, some constant time, constant number of additions, multiplications, subtractions, divisions, okay, which is in our language is order 1 time. So, given any pair of line segments, these are basically primitives that we take for granted whenever you are solving any geometric problems. So, the good thing about the simple thing about the previous problem, maximal problem, was that the only operations we are using was comparisons. Okay, we are still in the old nice algorithmic framework that only comparisons. Here, unfortunately, we have to solve these using division, multiplication, and then there is this problem with overflow and floating points and so on and so forth. But as I said, we will not discuss those issues, the floating point issues. Okay, we will just keep them aside. So that can be done in constant time. Okay, so that is the basic primitive. Now, of course, we are not given one pair, but we are given n line segments, and I want to report all the intersecting pairs. Right. So, what would be the most trivial approach to this? Yeah, okay, fine. So, the first attempt would be check all n choose 2 pairs, just enumerate them. And to check every pair, we know that it takes constant time. We just discussed that. So, that implies order n square. So, we have the first attempt, or the simple straightforward approach would be order n square, the operations, let us say. Now, at the end of the algorithm, it may turn out that maybe all the segments actually intersected. So, there are n choose 2 intersection pairs, right. All segments can intersect, right, in a simple situation. Sorry, that is not the way. You can have everything intersecting essentially. You can always have cases like that, easily construct cases. That is one possibility. The other case could be none of them intersected, they are all disjoint. So, it can have the entire spectrum again. Right. So, you can have all the way from n choose 2 intersections to 0 intersections. Right. How do we argue that this simple naive algorithm, whether it is good or bad? Do you think you should be satisfied with this, or there is some shortcoming? Yeah. So, it is good if most pairs actually intersected, right, because the output size is about n square. You can't do anything better than n square, right. You have to report all the intersecting pairs. So, you are bounded by the output size, and therefore, n square algorithm is absolutely fine and acceptable if there were many intersections, right. But in the situation that there are hardly any intersection, then what are we looking for? We just made some redundant checks of every pairs. Okay. So, there are no intersections to report in the end. So, we are certainly not bounded by the intersection size. Right. So, we should then aim for something that is much superior to n square, okay, possibly linear time or whatever. So, we again have this spectrum of the varying output sizes, and because we have just seen in the prior example, we can using some clever techniques exploit the fact that output can vary, and we can make the algorithm somehow sensitive to the running time, sensitive to the size of the output, actual output. Right. So, this again, this problem is another one which kind of begs for this kind of approach, that we should be very careful, because it is a huge variation from order n to order n square, from number of intersections from 0 to n square. So, the running time cannot be better than order n. So, it could vary all the way from n to n square rather than just from n to n log n. After all, the previous example was only about n to n log n. You may not be so much concerned about that. Here it is all the way from n to n square. Okay. So, then we should be really careful. Okay. So, how do we then address this? Okay. Okay. So, let me do one thing. Let me switch over to a slightly larger paper. Okay. So, I will switch over to this one and leave this aside. I can draw it more easily here. Okay. Okay. So, I have these line segments. Should I? Let's try to. At least pretend they are the same. Okay. So, we have something like this, this, something like that. Yeah, can we switch to this? No, so I had told them that. It will be difficult for me to actually, this is a smaller place to write. Can someone just warn them that they said they will keep a watch. Yeah. Okay, let me try to draw this anyway. Good. Okay. Fine. So, this is now visible. So, let me shift over here. Right. And the reason I want to shift over here is that you can actually view my hands and everything, unlike my tablet. Okay, and I need that. So, for the line sweep actually, so I am trying to basically explain how line sweep will be used in a problem like this, and what is actually line sweep. So, somehow we need to order the points like we did in the case of two dimensional maxima, that either we start from the maximum x coordinate and move towards smallest x coordinate, or some coordinate axis. So, here we will do we will actually start with the lowest x coordinate and move towards the highest x coordinate of what? The x coordinate of the endpoints of the given line segments. That is the information that we have. Right. So, let us say that every segment, okay, S I, okay, is represented using, let us say, x I left, y I left, okay, and x I right and y I right. Okay. So, this is basically the representation of the line segment S sub I. Okay. So, some segment will have the lowest left. Okay, again let us assume that we do not have vertical line segments. Even if we did, we will rotate the coordinate axis and make sure nothing is vertical. All right. So, then we will start from the lowest x coordinate. Okay. So, in this case, line segment 1 has the lowest x coordinate. Okay. So, this is actually by this thing, it is x 1 L and y 1 L. Okay. So, this is the endpoint, and this is let us say the smallest x coordinate. So, when I say we start from here, we actually hypothetically what I am going to do is actually I will take a vertical line, okay, starting to the left of the leftmost point, okay, and pretend that basically I am moving it and translating that vertical line from the left to the right. Okay. It is like essentially I am taking snapshots, okay, as I move from left to right. So, at any point of time, my snapshot is the intersection of this vertical line with the line segments. Okay. So, if my vertical line is where this pen is, the snapshot essentially are these two line segments 2 and 3. 2 and 3 intersect this line, vertical line, nothing else does. Okay. So, similarly, if you think about this line sweep in higher dimensions, okay, again it will be a cross section where we can sweep, let us say, from x to again if you sweep along x axis, the y and the z coordinates will be basically the cross section. So, at any point, so that will be a plane instead of a line. Here the line sweep is actually a vertical line, there will be a vertical plane. So, whenever we do this sweeping, okay, the information of the snapshot is the intersection of this line or the plane with the input. Okay. So, when we start from the leftmost to the left of the leftmost point, well, we are not going to start from minus infinity, because there is no input there and there is going to be no interesting information there. So, essentially we begin where there is some interesting input. So, we will start from the leftmost endpoint, okay, and move all the way to the rightmost endpoint. So, that is the way the line sweep will work. Okay. Now, as we move this line, of course, I am saying we are moving it in a continuous fashion, we will not be able to sort of actually simulate this thing, because it will take infinite time. A continuous moving line will take infinite time. So, we will only take snapshots, at some junctures, okay, which will be interesting to us, and these are called event points. Okay. So, I am using the word snapshots. Okay, and I will be interested in the snapshot only at the event points. I will tell you what the interesting events are, and that will depend on the context of the problem. So, in the context of this problem, I will be able to tell you what the event points are. So, as we sweep this thing, the line or the plane or whatever, okay, again not really sort of simulating this continuous thing, but only looking at what the changes happen at event points, we will be recording the changes at the event points. Okay. And using those recording only at the event points, somehow whatever information we accumulate, okay, will be enough for us to solve that particular problem. Okay. So, I am trying to give you a very high level sort of description of what line sweep method is. Okay. And it is a geometric method, because we are talking about leftmost and rightmost and intersections and so on and so forth. So, it is clearly useful for geometric problems. Right. Okay. So, in the case of that maximal problem, if you think about it like a line sweep, where we swept from the highest y x coordinate to the lowest x y coordinate, what do you think is a snapshot there?
The endpoints of those the line segments.
Yes, stairs, but what is the intersection of the stairs?
So, the next point which is higher than the
exactly. So, if you just think about it, there was these stairs, right, okay, and if you sweep a line, okay, at any point of time, again it is a vertical line, but just the being swept from right to left instead of left to right. So, when it intersects, it just intersects this staircase at one point, and that is nothing but that highest y coordinate to the right of that. So, at any juncture, the highest y coordinate is what is being recorded, and that is a snapshot. Okay. So, without even getting into the nomenclature of the line sweep, okay, we actually devised a method, or we used a method that is essentially a line sweep method. Okay. It is just a very elementary line sweep method, because the problem itself was a simple problem. Okay. But for this problem, it will be slightly more sophisticated. All right. So, okay. So, now let us see what we need to do in the context of this problem. Okay. So, when I hit the left end point, okay, there is not much to do. I mean, just this one line. Okay. Only when we are in a situation where there are more than one line sort of crossing the vertical line, things start become interesting, because now we know that we have more than one segment in the input, and therefore, there are some potential or possible intersections. Okay. So, what we note, again I am saying the snapshots are that at any juncture I will basically record the intersection of the vertical line with the line segments at any given x axis. Okay. So, if I call this L, the line as L, okay. So, the intersection of the segments with the line at any coordinate x, okay, let me call it else of x.
Can we rename the endpoints or the intervals of x axis, so that point is integral? I mean, there is
Not necessarily, you know. So,
without
it depends on what kind of fractions you are using. So, that is not clear. You know, it is not something that we can always do. What you are saying that given a, you know, so this is real numbers, right. So, how do you even you know you can so it may even be irrational, right. So, it just makes life really very hard. So, let us not get into that. So, whatever we are given, whether it is real numbers, we have to deal with real numbers. The integer, if the input is integer, then it is fine. But if the input is real number, no, you can't say that I can convert it always into an integer. So, it can also be rational numbers. It is not even simply multiplying with something and making it large enough, right. But you know, this algorithm will not depend on any of those things. You know, it's a combinatorial kind of an algorithm, and you know, you will not really, you know, bother about the floating point nature of the inputs. Right? So, else of x is the intersection of this vertical line or the line sweep, the sweeping line with the line segments at coordinate x. In fact, what I will do is I will use else of x to denote the sorted order of segments as per their intersections. Okay. In other words, the else of x at this point would look like, for this thing, it will look like, so it first intersects 1 and then it intersects 2, right. So, let us say from top to bottom, I keep it ordered, whether it is top to bottom, bottom to top, it does not really matter, but just follow one convention. So, here else of x is going to be something like 1 comma 2. At this x, you know, else of x is 1 comma 2, because it first intersects 1 and then it intersects 2. You can calculate the exact intersection point, or you can simply keep record of the fact that, you know, there is this line segment 1 and this line segment 2, and you have the description of the line segment 1 somewhere and the description of the line segment 2 somewhere. Whether you want the exact intersection or not, that is not the point. It is the ordering that we are going to use. Right. So, at this point it is 1 2. As we keep moving right, what happens is that at the right end point of line segment 1, the line segment ends. Okay. So, here the just as you cross this, okay, then your, you know, suppose this I am calling some x prime. So, else of x prime is only now 2, right. 1 has disappeared, because 1 has gone. I mean, once you sweep past 1, 1 is gone. So, there is only one line segment in L x prime, if this is x prime. X prime appears beyond line segment 1. Right. You sweep further, and then of course, at this juncture, then again you have this line segment coming in. So, then it has to be revised, and then it will become so 2 appears over 3. So, it is going to be like 2 comma 3. Right. Then there is a problem. Okay, no, sorry. So, right after that, you know, you encounter 4, and 4 actually is the topmost intersection. So, then it should look like 4 comma 2 comma 3. So, that is how the ordering is changing. Okay. Till now, you know, the ordering were changing, we were only considering the endpoints, but then again the ordering is going to change here again, intersection point. Okay. So, the moment we cross the intersection point, the ordering is going to change as 3 is going to remain below everything, but the ordering of 2 and 4 will swap, right. So, then it will be 2 4 3. In fact, if I tell you that the ordering was 4 2 3 and the ordering is 2 4 3, you can immediately tell me that there is an intersection, right. Otherwise, there cannot be a swap. Okay. So, this is basically all that this line sweep is going to do. It is going to record, you know, these orderings as we sweep from left to right. Okay. And the event points, now you should be able to guess what the event points are. So, the event points are exactly those where orderings change. Well, orderings change means basically L of x changes, whether something disappears or not, that is also a change in ordering. Okay. So, we want to record everything about where the orderings have changed, whether it is due to the insertion or the end of a line segment or by intersection. So, there are three kinds of event points. Okay. So, event points are three kinds: new segments, which is basically nothing but left end points, okay. New segments and segment ends, okay, right end point, okay, and then the most important thing, the intersection points. For us, at least in the context of this problem, intersection points are the events that we are really looking at. So, these are three event points. Now, what is the difference between these event points? If you just characterize, or are these all event points known to us? First two are known. The third one, the one that we are interested in, is obviously not known, because we wouldn't have run all this algorithm. We knew the intersections, we are done. Okay. So, somehow in the course of the algorithm, okay, when we are saying that essentially the job of this line sweep is to record all the changes at the event points. So, if we can actually perform this changes at all the event points, we would also know all the intersections. It is not that intersections are known to us, but the intersections will have to be discovered as and when we encounter them. Okay. Okay. So, in other words, what I am saying is, so event points must be known before we encounter them. Specifically, intersections. Right. The left endpoints, the right endpoints are known to us, right. And we want to also sweep and sweep them in order of the x coordinates of these event points, right, because we are sweeping in order from left to right. Okay. So, we need to somehow, because we want to discover them before they get known. So, at any point of time, at any juncture, we must have a sorted queue of event points. So, initially, of course, what is that we know? We know all the left and the right endpoints. So, my initial event point q is the sorted order of all the endpoints of the line segments. Okay. Initially, 2n endpoints, of course, sorted in the right order, sorted of n segments. So, this is my initial event queue, or event queue of these for this line sweep. Okay. And then I have to somehow, as we sweep, we should be able to insert the intersection points. Otherwise, if we miss the intersection points, then of course, our algorithm does not work. Okay. We have to be you have to precisely discover all the event points. Okay. So, how do we discover all the event points is what this entire algorithm is about. Okay. This is our initial event queue, okay. And you know that else of x is a sorted set of segments. Intersecting the sweep line at x. So, these are the two information that we will keep, right. One is sorting of the event points along the x axis. Okay. The other is the snapshot, which is the intersection of the line segments with the sweep line. Right. what we have observed, at least we have made one observation. So, if you go back to this, as we sweep across from left to right, any intersection that happens is going to switch the order of two line segments. Right. And not only that, you also observe that it is going to switch the order of two line segments. So, just look at the situation just before you hit the intersection, after the intersection. These two, the swaps must also happen between two adjacent line segments. Just look at the scenario just before you have hit the intersection point and just subsequent to the intersection point. The two segments that intersect, okay, necessarily must become adjacent before they intersect. Okay. So, we are not talking about arbitrary line segments trying to find out which of them are actually switching the order, but we just by looking at only the adjacent pairs, okay, we should be able to figure out or at least compute whether or not they intersect. Okay. And essentially what we are saying is that before two line segments intersect, which is the event point that we were interested in. Okay. So, observation before the intersection of two segments, say S I and S j, they must necessarily be adjacent in L sub x. So, this is the real crucial observation, and this is what is going to actually help us designing an efficient algorithm. See, the reason why we are stuck with that n square bound or n choose to bound is because we have no idea which two segments can potentially intersect. Right. But now, if you look at this L sub x, which is the ordered line segments, okay, we do not have to look at every pair of line segments, but we only look for adjacent pair of line segments, okay, to find intersections. Now, adjacent pair of line segments does not necessarily mean they will intersect, but they are the only potential intersections. Okay. So, at any point of time I do not have to check n square pairs, but I have to check only order n adjacency. Right. So, this is where the saving is going to come from. Okay. Again, so this was the input. So, as we sweep across, 1 and 2, well, this is a simple case, but let us say this particular intersection 2 and 4 have become adjacent before they intersected, and then look at again 4 and 3. So, 4 and 3 of course, again became adjacent before they intersected, before this intersection point they had come together. Okay. And when they have come together, that change must have occurred in the previous event point, because we are saying, let us say inductively, that we will maintain this invariant that we are recording all the possible orderings, all the orderings of the event points. So, when they came together, that must have happened because of some previous event point. So, if our algorithm was inductively right up to that point, then we should have recorded this, and therefore, the moment they come together. Okay. So, this is what we are going to do. The moment we find two new line segments are adjacent, we will check for potential intersection. Okay. So, at any event point, we will check for potential intersections between two segments that have just become adjacent. So, previously they were not adjacent, but they have not just become adjacent because either we have inserted a new segment or deleted a new deleted an old segment, okay, or because of intersection also there could be new adjacencies created, right. So, if you look at this example, as we sweep from left to right, okay, the moment I encounter 2, 1 and 2 are adjacent. So, what I must do is find out if there is an intersection between 1 and 2. Okay, there may or may not be. So, if 2 had ended here, there would not have been, but of course, in this case it is. So, this we can check. Okay. So, then we go past this and 1 disappears. Okay. but because of that there is no new adjacency created in this case. Okay. Then I sweep, I reach 3. The moment I reach 3, I know that there is a new adjacency between 2 and 3. I must check whether there is an intersection between 3 and 2, and actually there is no intersection, but I am checking that. Okay. Then I encounter 4. Okay, 4 has become adjacent to 2. So, I must check for the intersection between 4 and 2, and actually they do intersect. The moment it intersects, I discover that intersection point and I actually insert it into my event queue, because I know that there is an intersection and that is an event point, and therefore, I will record that event point. Okay. So, after I record that event point may have happened much later. This intersection could have happened here also, but whatever event queue I have at that point, I will insert that event point in the right order. I must maintain the sorted x coordinates of the event points. Okay. The moment I discover there is an intersection, I am going to insert it into the event queue, okay, and then continue the line sweep. So, here actually this event point of intersection happens is the next event point. The moment there is this intersection, these 2 line segments have been swapped, okay, and therefore, I must check for adjacency between this and this line segment, that is 4 and 3. Okay. So, whenever there is these event points, there are some new adjacencies created, but you see how many adjacencies are created at any event point. Yeah, some constant number. Okay. So, that is what will be the essentially the way I mean that will be the saving thing. For the entire thing, now you can kind of see that we are not going to the number of event points is how many? The total number of intersections plus 2n. Okay. That is nice, that is the output size, and at every event point there is only some constant amount of processing that we have to do. At least we are checking for some constant number of adjacencies, right? Yes.
So, in this continuous line sweeping, obviously you are showing as if x is evaluated, but here in some discrete point you have to now, when the intersections come, before that, I mean when it is going continuously, you can see that magically before that you have this number, and after that, but how, at what point exactly you will evaluate at what x?
The changes. So, what is the change? The change in L of x is only the ordering, it is not the exact intersection point. Yeah. So, the ordering can change only at the event points, and if I am inductively doing everything correct up to a certain event point, then the next thing also will be done correctly.
But you are not able to evaluate on the intersection, because you do not know, you can evaluate on the
no, but
left end of point or the right.
Okay, the question is the point here is that we are going to discover every intersection point before it occurs, because they have to become adjacent before they intersect. And how did they become adjacent? Because of a prior event point.
Okay, at the point they are intersecting, now you are using the intersection actually to.
The actual intersection is an event point for me. So, my next stop.
After you go there, then
no. My next stop is whatever is the event point. It could be an intersection point also.
So, at that point you are actually checking all these.
Yes. So, the total amount of processing that we are doing is about constant modular data structures. Okay, so we haven't talked about data structures. Yeah.
So, suppose just in the beginning only all the lines are there in your queue, such as the example.
Right.
And in that case, suppose there are long lines and they still remain in and they intersect somewhere in the past.
Right.
Actually, what happens is then at the beginning only you need to check whether they intersect or not, or something like that.
Yes, you have a point, and I will take that issue tomorrow. So, it can be easily handled. I will take it up tomorrow. So, the question here is the following, that suppose we actually had lines, very long lines, so that there were actually these n square intersections, n choose 2 intersections. Now, I am always maintaining that but let us say that
there need not to be n choose n C2 intersections,
but a large number. So, you are asking me where are we going to begin from, right? But then again it cannot, the intersection point cannot happen before the leftmost endpoint, and it cannot happen after the rightmost endpoint. So, I already have a finite size box or whatever region to sweep.
But you said as soon as we reach some event point, we need to check whether there is an intersection being.
Is there a potential intersection? Yeah.
I am saying just that in the beginning only all the lines get inside.
That is fine, but my first event point has to be the leftmost endpoint. Okay, and the moment I sweep past that and reach the next line, I would have discovered the first intersection point, because it cannot occur before the two So these are singularity conditions that we can deal with by just rotating the axis. Okay. So let's stop today here. Okay, we'll carry on the discussion tomorrow.